Hi everyone, today we're going to do a little more practice. This is Midterm 1 from 2018 when Dr. Jaw and Terry Gullen were teaching the course. So what I'm going to do is just whip through this midterm and hopefully get it done quick. Alright, first question says, what is the hybridization of all of the atoms indicated with an arrow? Put the answers in the boxes provided. So what we need to do for each one is take a look at the number of electron groups. First one I see is this nitrogen, where there's a double bond, a lone pair, and a single bond. That's 3 electron groups total, meaning this is going to be sp2. Carbon below it has 2 double bonds to it. 2 electron groups makes it sp. Next carbon along the chain here has 2 bonds to hydrogen, a bond to nitrogen, a bond to carbon for 4. Makes it sp3. Next carbon beside it, a double and 2 singles, is sp2. Next carbon here has 4 single bonds for sp3. Lastly, we have a single and a triple, which is sp. Number 4, draw Lewis structures for 2 of the 3. We'll be overachievers and do all of them. So NO2, the central atom's typically listed first. So we'll do this. We'll add up our valence electrons. Nitrogen gives us 5. Oxygen gives us 6 times 2. And the positive charge gives us -1. So that gives us 6 times 2 is 12, plus 4 is 16, minus 4 for the 2 bonds we've already drawn gives us 12. We use the 12 to fill the octets of the outer atoms first. We used all 12 and we're left with 0. We now must make multiple bonds in order to cause the central atom to have a full octet. This gives us N, O, O, double. And finally, we want to assign formal charges. The nitrogen will have a formal charge of its valence electrons, which is 5, minus the number of bonds, which is 4, minus the number of unshared electrons is 0, plus 1, plus. The oxygens are both neutral. So that would be our preferred structure. Next, CO3H2. So this you might need a little bit of help with. Carbon is going to be central. We're going to have bonds from carbon to 3 oxygens, and 2 of those are OHs. Now technically, this could have a second structure, which is CHOOOH. I'll finish that one off later on. But this one we will have, in terms of number of electrons, the oxygens will give us 6 times 3. 6 times 3. Hydrogens will give us 2. Carbon gives us 4. It's going to be 18. That gives us 24. From the 24, we have to subtract 2 for each bond we've already drawn, which is 3, 4, 5, which is 10 electrons, which is 14. Fill outer octets. 2, 4, 6. Now we do the oxygens over here. 8, 10, 12, 14. Used all of our electrons. Carbon in the center does not have a full octet, so we can bring a pair down. And if we do that, we will get a double bond between those 2 atoms, and you will have a molecule of carbonic acid. If you do the structure that I showed you below, you still have 14 to place, and we could then bring them down to give the full octet to the carbon, and we get a double bond here. So if it was me grading it, I would give you equal points for either of those. Both are actual real molecules. The bottom one is called a peroxy acid. And peroxy acids are actually not as rare as you might think. If you, what's that brand? There's a brand of washing OxyClean, I think, or Oxy something. Anyway, you can actually buy peroxy acids that can do cleaning. Yeah. Anyway, C2Cl2. So I would give this the structure Cl, C, C, Cl. Cls cannot be central atoms typically. I guess that's not true. They can be in molecules like chlorate. But here we're going to put the carbons central. We're going to count our electrons, and we're going to get 4 times 2 for the carbons. For the chlorines, we're going to get 7 times 2. The total here is going to be 8 plus 14 is 22 minus 2, 4, 6 for the 3 bonds. We've drawn 16. Fill outer octets first. 2, 4, 6, 8, 10, 12. Left with 4. Why don't we spread them evenly over these 2 carbons? That's used our 4, and we're left with 0. Now the carbons in the center do not have full octets, so we need to make multiple bonds. There's lots of different ways we could imagine doing this. We could either take both carbon down and go or we could draw in one of the chlorines. So you could imagine another one where you have Cl, C, C, Cl. And we could bring maybe one of these down and one of these down. And we get kind of an ugly looking structure if we do that, where you have Cl, C, C, Cl. Now, that's a legal structure, but it's not preferred, and the reason it's not preferred is because if you start assigning formal charges, what you will find is that this molecule will have a positive formal charge on the chlorine and a negative formal charge on that carbon, whereas the structure I drew first has no formal charges and will be the preferred structure in this particular example. All right. Next question. Draw 2 additional resonance structures for each of the following in the boxes provided. More than 2 may exist. Circle the more important, most stable structure, biggest contributor. You can show all hydrogens and carbons. Draw curly arrows in the original structure to show the flow from second, and so on. Okay, so what I see in this first structure on the left is a cation. A cation, you can think of it as almost being like a hole where there's no electrons. If we wanted to take the advice over here and draw in all of the hydrogens, let's do it. That's a CH3. This is very helpful because it can prevent you from pushing electrons where they can't go. What you do is, if there's a cation, often is look for an adjacent atom with a lone pair, or an adjacent atom that's making a double bond. In this case, the cation has an adjacent atom with a lone pair, which is the nitrogen, and you could bring that down. If you do that, you will make a structure which looks like double bond here. We're going to continue to draw in our hydrogens. And now we have a plus formal charge on the nitrogen. Okay, so that's not a bad structure. You have a positive charge on a half electronegative atom, like nitrogen, but at least everything's got a full octet, which is more than you can say for the original structure. Is there anything else you can do? Well, sure, we still have a positive charge on nitrogen, so we can push electrons towards it. We can push the ones we just made the double bond with back, and if you look at the other double bond, we can push them one step over as well. So you end up with a structure that looks like this. We have Now our lone pair back on the nitrogen. Now that positive charge has to go somewhere, and if you look at this atom right there, it has 3 bonds. All the hydrogens are shown because we drew them in, and that's it. Only has 6 valence electrons, does not have a full octet. So the formal charge of that carbon is 4 valence electrons for carbon, minus 3 bonds, minus 0 unshared electrons is plus 1. So we can put a positive charge right there. Next, we have this structure here. This one's a bit different. Instead of starting with a cation, we're starting with an anion. So think of an anion as like an excess of electrons. So what we want to do is push them somewhere. We can push them either to the right, up into the carbonyl oxygen, or we can push them to the left, into the carbon double bond nitrogen. I'm going to start with the right. We can push those down to make a double bond there. We can't just do that though, because if you just push them there and stopped, that would mean you have 5 bonds going to the carbonyl carbon. So we're going to, at the same time, pull a pair of electrons up. Everything else we're going to leave. This now becomes a double bond. There is a hydrogen here, which we can continue to draw in. That bond to oxygen becomes single. That's a CH3. And the oxygen now has 3 lone pairs and a negative charge. It had 2, and we pushed a pair up onto the oxygen, which gives it a 3rd one. Now we want to draw another structure, which again we start at the negative charge. We're going to push those back down, and what we can do is push those electrons towards the nitrogen, the other double bond. Pop them over there and pop them over here. What you end up with then is CH3 and CH3 double bond hydrogen. Our carbonyl is back. Now our nitrogen had a lone pair, and we just pushed another pair of electrons onto the nitrogen, so it gets a 2nd lone pair. And if you look at the formal charge on the nitrogen, 5 electrons, valence electrons for nitrogen, minus 2 for the bonds, minus 4 for the unshared electrons is negative 1. So that nitrogen gets a minus 1 charge, and this is our 3rd possible structure. And I think that's it. It didn't want the electrons back to the first. No. So that's it for that. Question 3 says, what are the chemical formulae, i.e. C6H12, whatever, for the following bond line structures? So this just is making sure that you count correctly everything that's there. So this has a carbon, 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 so it'll be C5. It's H3, there's a hydrogen there not shown, hydrogen, hydrogen, H3. That becomes 3, 4, 5, 6, 7, 8, 9, Br. This is just testing to make sure that you can tell how many atoms there are that aren't shown in these structures, and maybe your basic counting skills as well. This becomes CH3 hydrogens. There's 2 hydrogens on each of the ring carbons, except for the ring carbon with the positive charge. Nitrogen will have a lone pair. How do we know nitrogen doesn't have any protons? There's 2 clues. One, for bond line structures, we draw hydrogens that are attached to non-carbon atoms. Second, if nitrogen had a hydrogen on it, it would have 4 bonds and a positive formal charge. It doesn't have a formal charge. Now that carbon, in order for it to have a formal charge of 1, it's 4 minus the number of bonds minus the number of unshared electrons, which is 0. So that means there has to be 3 bonds in order for it to have a +1 charge. Only 2 are shown, so there's 1 more that's not shown. This is not a CH2, it's just a CH. Okay, so what does that mean? Well, we have 6 carbons, right? 1, 2, 3, 4, 5, 6. And we have hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. N. Get that right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For each set of molecules, circle the one with a higher boiling point. Name the strongest intermolecular force each will have. So this one is nonpolar. Let me get my blue back. Nonpolar. So all this would have is dispersion. Small molecule, so dispersion forces will be weak. This one has a quite polar carbonyl group. That gives it dipole-dipole. So I guess why is there 2 categories? For each set, circle the ones with the highest boiling point. It's one I've already circled. Each compound. Okay, so this is going to be dipole-dipole. And this is going to be dispersion. All right, second example. NaCl is an ionic compound. So the intermolecular force here, I guess, is just ion-ion. Although this would be NaCl dissolved in solution, because NaCl is a crystal. We typically call that ionic bonding as opposed to ion-ion intermolecular forces. Very small point. NH3 is ammonia. NH3 has 3 NH bonds, which give it hydrogen bonding. Which has strongest intermolecular forces? NaCl by a long shot. Ionic bonding is very strong. You have to heat NaCl up to over 1,000 degrees, I think, to melt it. NH3 boils quite readily. Next we have cyclohexane, which has only dispersion. Nonpolar. CH2Cl2 is polar, so it has dipole-dipole, but it doesn't have hydrogen bonding. Nevertheless, dipole-dipole is stronger, so you'd think this would have a higher boiling point. Circle and label all the functional groups in the following molecule, primary, secondary, tertiary where appropriate. Here we have a carboxylic acid. Here we have a CN, which is a nitrile. Here we have an alcohol. Here we have an alkyl halide. This is secondary, by the way. So is the alcohol, because the carbon that has the OH has 2 carbons attached to it. The bromine with the carbon has 2 carbons attached. It's secondary as well. That's an alkene. This is an amine. This is an ether. This is an amide. For any 2 of the following, circle the weakest base, should be weaker base, and explain why in the space provided. All right, so the weaker one is going to be the one that's more stable. We have an oxygen-centered anion versus a sulfur-centered anion. If you think about their conjugate acids, this one is going to have an OH, this one is going to have an SH, right? Stronger acid would be SH, meaning its conjugate base is going to be a weaker base. That's because S is a larger atom than oxygen. It can better handle charge compared to oxygen, because sulfur and oxygen are in different rows of the periodic table. So how would I describe this? I would say that the B is a weaker base, because S is larger, 1 row down, . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . and can better accommodate the negative charge. You can think of it as the negative charge is spread over a larger volume, and we know that charge does not like to be concentrated. So sulfur, it's concentrated less. Second example, we have two O minus, two alkoxides, one where we have tertiary and one where we have primary. This one's a little more subtle, but what we know is that alkyl groups like CH3 can donate electron density, right? They are donating electron density that way. Probably shouldn't use a dipole arrow here. But they are pushing electron density into the oxygen, and that causes more charge to build up on the oxygen. So this one actually is a less stable ion because you have three alkyl groups, because it's tertiary. You have 1, 2, 3, pushing density into the oxygen. The right-hand one, we only have 1. So the more stable one is the weaker base. D is more stable. Therefore, weaker base, because C has 3 electron donating groups, alkyl groups, donating electron density, which destabilizes C. All right, E versus F. We have either an oxygen-centered or a nitrogen-centered anion. And what you can tell if you look at the top row of the periodic table, well, I guess the second row, you have boron, carbon, nitrogen, oxygen, fluorine. Electronegativity increases this way. When you're comparing bases that differ by the atom with the charge being different atoms, but in the same row of the periodic table, you go by electronegativity. So we would say that E is more stable than F because oxygen is more electronegative. And can better stabilize, that's what that word is, the negative charge. Because E is more stable, E is a weaker base. For all of the following, add in all of the missing electron pairs. Okay. In the box under, write A or B to identify if it's an acid or base. 3, draw the mechanism curly arrows. 4, for each reaction decide which is favored. All right. Lone pairs first. We want to give everything an octet. Hopefully you can see those little dots going in. I'll make them bigger over here. The oxygens we need to give either 2. That carbon needs a pair of electrons to give it a negative formal charge. So what's going on here is this is acting as an acid because it's donating hydrogen, which is gone in the product. This is acting as the base. And for the reverse reaction, this is the acid and this is the base. Draw the mechanism's curly arrows on the left-hand side to see what's going on. So the base on the left side is forming a new OH bond. So we need to start our arrow at an electron pair, and we're going to move that to the hydrogen that disappears. Well, it doesn't disappear, it just moves to the other atom. And the CH bond breaks, the pair of electrons go to the carbon, and you get a lone pair on the carbon. And lastly, decide which one is favored. So basically what we do is we find out which side has the stronger acid or the stronger base. The side with the stronger acid or stronger base will be disfavored. So looking at the two bases here, we have either an oxygen-centered anion with resonance, or we have a carbon-centered anion with resonance. Oxygen is more stable, so the stronger base will be on the right-hand side. So that means the left is favored. I guess what do? Circle left. Left side is favored because the weaker base and the weaker acid are on that side. Next, lone pairs. We just need one lone pair on that carbon, and we need one lone pair on that carbon. And so this is going to act as our base. This is our acid, this is our base, and this is our acid. So what's happening is this will grab the hydrogen, and the lone pair goes to the carbon. That gives you this structure, and this now has a CH bond. The more stable base is this, because that carbon is sp versus this carbon, which is sp2. So the stronger base is going to be the left-hand side. That means this is going to favor the right. Is there something else I forgot to do there? No, that's it. Pairs, arrows, circle left or right, and A and B on the bottom. Label the two orbitals that are overlapping to form the sigma bond below, indicated by the arrow. So that carbon is sp3 hybridized. This carbon is sp2. So this would be an sp2, sp3 overlap. What is a diagnostic 2-atom stretch, not alkyl CH, that we would expect to see in the IR spectrum for this compound? Be specific in a range in centimeters to the -1. So one at least might be a carbon-carbon double bond. CC double bond stretch, and it comes around like 1650, I guess, centimeters to the -1. Usually we give you a chart with written tests. Sometimes it's included in the document, sometimes it's not. I can see this time it's not included in the document, but that's where you could look up the specific ranges for these. The other one that you might expect to see would be NH2. And the exact numbers for these ones, just give you a second because I have to look that up myself. So an amine, it comes up on the sort of the left-hand side of the spectrum. And look at that, our table gives an amine stretch at 3300 to 3500 reciprocal centimeters. Great. Draw the most and least stable Newman projection conformations of 2-fluoropentane viewed down the C3-C4 bond. C3 is the front. So 2-fluoropentane, you can draw the compound. 1, 2, 3, 4, 5. And 2 is the fluoro. And 1, 2, 3, 4, 5. And we want to look down the carbon-3, carbon-4 bond. And it says 3 is the front, so that means our eye would be kind of here, looking in that direction. So what that means is looking at conformation. I'm going to take a little bit of space up here before I write my final answer in the space given. That means the back atom is a circle, the front atom is a dot. So on the front atom, which is carbon-3, big atom is 4, 3 also has 2 hydrogens. So on carbon-3 we're going to have a hydrogen, we're going to have a C HFCH3. Actually, maybe what I'll do, instead of writing all that out, is I'll actually draw the thing. So this is C2, C1, F, Got another hydrogen here. On carbon 4 has a hydrogen, and a methyl. Hydrogen, methyl. Now the one I have has the two bigger groups, gauche, which means it's not the most stable conformation. Most stable will be anti, so I'll draw that as an anti like so. I'll leave the front carbon the same. But the back carbon I'll rotate around. So the two big groups are anti to each other. Least stable would have them eclipsed. Again, we can leave the front the same. I guess I flipped the fluorine, but that's okay because that's a single bond that can rotate. Hydrogen, hydrogen. Spin the methyl around. And you get this conformation. B, draw the structures for 2 given the IUPAC names. If more than 2, first 2 will be marked. 2-chlorobutane. That was easy. 4-methyl cyclohexanol. And 1 always goes to the carbon with an oxygen. 4-methyl. Triethyl hexane, 3,3,4. Hexane is 6. And we have 3, ethyl, and 4. Next one, 2-methyl butane. Butane we draw first. We draw 3-chloro, 1-fluoro, 2-methyl. Those are good questions. Those are giveaways. Match the IR spectrum. Match each IR spectrum to the structures by writing the corresponding letter in the box. So we look at each one and see what we see in the spectrum. We see this big ugly thing over here, which to me suggests carboxylic acid. That goes along with having a C double bond O. So I would look in the list. I see alkyne, I see alcohol, carboxylic acid, and alkane. So C is the first one. Alcohol is one though. Alcohol should be easy to find. It gives a broad peak around 3,500, 3,400. And you can see looking at these spectra, this has one and this has one, but the bottom one is broad and this one is sharp. So the broad one is going to be our alcohol B. That's all it wants. Okay, we have 2 more. We have an alkane left and we have an alkyne left. Alkyne should give you a CC triple bond right around here, 2200 reciprocal centimeters. This is a terminal alkyne. It comes at the end of the chain, meaning it terminates in a CH. That CH is what gives that sharp peak here. So this one is A. And by default, this one is D. But there's not all that much going on here anyway. You know, we can draw a vertical line at 1600. This is all fingerprint. We basically see nothing here except for sp3 carbon hydrogen stretches. All in all, not too exciting. Unclear answers will be given 0. Scary. Multiple choice. What is the definition of a Bronsted acid? It's a proton donor. C. Formal charge on the oxygen on the following molecule. How do you find formal charge? You take the number of valence electrons oxygen normally has, subtract the number of bonds, subtract the unshared electrons, and you get +1, which is D. Which of the following molecules is a resonance structure of the original? Well, C is not because it has no charge. If you do pop, pop like that, you would get B. Not D. D's no good because there's a hydrogen here that has a pentavalent. You can't push electron pairs over here because that's a CH3, so A is out. E, no. No. If you wanted those electrons to go over, you'd have to have the charge on that carbon, not the carbon indicated. B is the correct answer. Which of the following molecules are constitutional isomers? So what you can do here is come up with the chemical formula for each. This has 1, 2, 3, 4, 5, C5, H3, 6, 9, 10, 11, Br. This one is C4, H3, 6, 9, Br. This one is C5, H 2, 4, 6, 8, 9, Br. Close to that one, but not quite. A, we have C5, H, 3, 3 is 6, 1 is 7, 8, 9, 10, 11. So it looks like A and D have the same molecular formula, so those are isomers, and that is D. Which of the following statements is true? If a molecule contains a polar bond, the molecule is polar. No. A molecule like CO2 has polar bonds, but is non-polar. Ion-ion intermolecular forces are weaker than ion-dipole. That's also untrue. Ion are the strongest. Chemical's boiling point depends on its intermolecular forces. That is true. A CF bond is not a polar bond. Nope, it's ridiculous. Conjugate base, no, that's its conjugate acid. So C I'm satisfied with. The smaller the pKa, the stronger the acid. Certainly not friendlier. It's the opposite of friendlier. Prettier, funnier. Yeah, weaker, stronger. Definitely lower the pKa, the stronger the acid is. In fact, the strong acids we're familiar with, HCl, H2SO4, they have negative pKa's. The pair of compounds that is correctly ordered from highest to lowest boiling point. Oh, God. Okay. This one has 4 carbons. This one has 3. So I would expect stronger intermolecular forces and higher boiling point for this one. So that's not right. It's saying it's less. It should be greater. B, these two are the same compound. Both of these are butane. So they're equal. Next, we have pentane versus isopentane. Isopentane has a lower boiling point, and that's because it is lower surface area because it's more spherical in shape, higher branching. Next, we know cycloalkanes are higher boiling point than the linear ones, so D will be our correct answer. And E, definitely, this one has a higher boiling point, so E is wrong as well. Type of strain that is minimized when a Newman conformation is staggered, not eclipsed, is torsional. A. For these kinds of questions, go to the Instagram. We got lots of good examples of these. What's a correct Newman projection for 1-chlorobutane looking down the C1 bond? This one's definitely out. It's got way too many carbons. Okay, looking at these, we can have 1, 2 is the big fat one there. 3, that's 1-chlorobutane. So this one's a candidate. C, we have 1, 2, 3. That's also chlorobutane. This one, we have carbon 1, carbon 2, carbon 3, carbon 4. Oh, these are prop. Only 3 carbons. So no, these are not. So A, B, C are all out. This is actually butane. This is looking down the carbon 2, carbon 3 bond. This last one, 1, 2, 3, 4 is E. This is the only one of them where you're looking down the carbon 1, carbon 2 bond. Rank the following acids in order of increasing acidity. 1 and 3 will be higher than 2 and 4 because They are OH acids that if you deprotonate gives a resonance stabilized anion. So we want the two with the strongest acids being 1 and 3. So let's cross out E, cross out C. Oh, this is easy. Strongest acid is D. The stronger of the two, 3 is going to be stronger than 1 because the electronegative fluorines further stabilize the conjugate base. After that, so it'll go strongest is 3, followed by 1, then followed by 4 and 2, but 4 will be stronger than 2 because 4 has electronegative chlorines which would stabilize the conjugate base there. 11, which is the strongest base, we see A having no stabilization by chlorines, so if it's not stabilized, it will be stronger. All of the other ones experience some degree of stabilization by having the chlorine nearby. Chlorine can withdraw electron density by the inductive effect, stabilize the anion, make it a weaker base, which is not a constitutional isomer of cyclohexanol. So cyclohexanol is C6H12O. We want to find another one that's C6H12O. My feeling is to look at D. We have 1, 2, 3, 4, 5, 6. C6H. We have 3, 2, 1, 2, 2, 2. That gives us 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, O. That is a constitutional isomer of cyclohexanol. Actually, we can do this for each one of them. And what you find is this is C6H12O, this C6H12O, C6H12O. This one is not. That's C6H14O. Which of the following could be correctly described as having two methyl groups gauche to each other? That jumps right off the page is E. The relationship between these two is 60 degrees. These are gauche. Which of the following molecules is polar? This is a tricky one. You have to draw a bunch of Lewis structures. It turns out all of these, well, CO2 is nonpolar because the bond dipoles cancel. CS2 has the exact same structure. Bond dipoles cancel. SO2 you'd think falls in the same thing, but if you draw out the Lewis structure, you actually get something that looks like this. And so the shape here is bent, and you end up with a net dipole for C. A and B also have symmetric shapes that cause any bond dipoles to cancel out, which will form an intermolecular hydrogen bond with diethyl ether. Diethyl ether has this. It can act as a hydrogen bond acceptor only because it has no OH or NH bond or FH bond. So we need something that can act as a donor, and the only one with a hydrogen bond donor there is D, which is the OH. None of the other ones can. The nitrogen, by the way, has a lone pair there, no hydrogen on that nitrogen, so it cannot. Which of the following contains a ketone functional group? This one's an ester, B is a carboxylic acid, C is an aldehyde, D is an amide, E is the correct answer. As the number of carbons in a straight chain alkane increases, its boiling point increases because it does not increase polarity, it does not create a dipole moment, it does not have anything to do with rotational degrees of freedom. Increased surface area, increased opportunity for induced dipole forces. That's true. Size doesn't matter in this case. It's increased surface area, and I would add increased number of electrons. Which is false. Increased branching among isomeric alkanes leads to lowering of boiling point. That is true. B, increased branching among isomeric increases instability. No. Branching causes it to be more stable. Cyclic alkanes have higher boiling points than their linear counterparts. That is true. So this is saying which one is false. So I must have jumped too quick on that. Among intermolecular forces, hydrogen bonding is stronger. Generally is. Molecules with polar bonds may be nonpolar. True. Increased branching among isomeric alkanes. Yes, that is true. Increased branching among isomeric alkanes increases instability. It decreases stability. Sorry, increases stability. So it doesn't increase instability. It's like a double negative, but yeah. B is the answer to that one. Curved curly arrows are conventionally used to illustrate movement of electron pairs. A. Which of the following has the most ring strain? I would look at A because it has a cyclopropane, which has 60-degree angles, and a cyclobutane, which has 90s. This one's pretty bad too, but not as bad as A. We are done. Look at that. Great. So that is the 2018 midterm. Hopefully I got 100% on this test. And that took me, how long did that take? I actually can't see my clock here, but anyway. Oh, I can. 46 minutes. That's not so bad. We would usually give you double that amount of time to write this length of midterm.